Welcome to the deep dive. Today, we're diving into, well, arguably the core of future energy storage. We're talking lithium, sometimes called the white oil.
It's a fitting nickname, definitely. I mean, the growth it's fueling is just exponential. For lithium batteries alone, lithium use hit an estimated 87% of total consumption in 2024.
Wow, 87%.
And that demand, it sent prices soaring.
Yeah.
You look at 2022, the average for battery-grade lithium carbonate was $68,100 per ton.
68,000.
Almost 6 times the price of just the year before 2021.
Okay, so that kind of price explosion tells a story. It suggests the easy stuff, the traditional high-grade ores and those rich brines, well, they're running out, or at least getting harder to access.
That's exactly what the source materials show. The industry is scrambling, is maybe a strong word, but certainly shifting focus, aggressively moving towards these unconventional sources.
Which means?
Which means things like low-grade brines and maybe most dramatically seawater.
Seawater, I know there's a lot of lithium in the ocean. A staggering amount, something like 230 billion tons globally. But the concentration is, well, it's incredibly low. We're talking 0.17 parts per million. Tiny.
Right, and it's not just low lithium, it's that it's swimming in a sea of other ions, right? Sodium, magnesium.
Exactly. Ultra low lithium and just tons of competing ions, sodium, potassium, magnesium being the big ones, makes extraction incredibly difficult.
So you've got this vast ocean, a tiny speck of lithium, and a whole mess of other stuff chemically similar. The old way, letting ponds evaporate for months, that's not going to cut it, is it? Especially with high magnesium.
Not at all. It's slow, takes up huge amounts of land, it's environmentally questionable, and yeah, high magnesium to lithium ratios basically render it useless for these new sources. We need something much faster, much more precise, surgical, really, and sustainable.
Which brings us to the core of today's deep dive.
Yeah.
Membrane separation technology, specifically lithium selective membranes, or LSMs.
Exactly. These LSMs are widely seen as, well, perhaps the most promising path forward. They can potentially cut extraction times from months down to mere hours. Yeah.
And cleaner too.
Much cleaner, yes.
Okay, so our mission today is clear. We need to really get into the weeds on these LSMs, understand how they work, what the different types are, the mechanisms they use for selection.
And critically, the trade-offs. There are always trade-offs in engineering these things.
Right. Let's start there. Why is it so hard to just pick out the lithium ions from that ionic soup? You've got sodium, magnesium, potassium, calcium, lithium all mixed together.
It really comes down to subtle differences at the nanoscale and how ions behave in water. There are two main approaches, two mechanisms for DLE, that's direct lithium extraction.
Okay.
The first is what we call the size sieving effect. Now, intuitively, you'd think lithium, Li plus dollar, should be easy. It has the smallest bare ionic radius, only 0.6 angstroms.
So just make a filter with tiny holes, smaller than anything else, like a molecular sieve.
Ah, if only. See, the complication is hydration. In water, ions attract water molecules. They wear a sort of hydration shell, or as you put it earlier, a winter coat.
And because lithium has such a high charge density packed into that tiny size, it holds onto water molecules really tightly. It actually attracts a larger hydration shell than the others.
Ah, the paradox. The smallest bare ion ends up being the biggest one once it's dressed in water molecules.
Precisely. So Li plus ends up with a hydrated ionic radius of about 0.382 nanometers. Compare that to sodium at 0.358 millimeters or potassium at 0.331 millimeters. It's actually the largest of the three when hydrated.
So size sieving based on hydrated size doesn't help you separate lithium from sodium or potassium?
Not effectively, no. To use the bare size difference, your membrane needs to be able to essentially strip off that water coat right at the entrance. And that requires incredibly precise structures, controlling dimensions at the sub-angstrom level.
Which materials can even do that?
This is where certain rigid crystal structures come in. Things like lithium-ion sieves, LISs, and especially inorganic solid-state electrolytes, or ICEs. Their inherent lattice structure can provide those precisely sized channels.
Okay, so that's size sieving, a very specific physical squeeze. What's the alternative if stripping the coat is too hard or inefficient?
The second main mechanism relies on binding affinity difference. Instead of physical size, we use materials that have a sort of chemical preference, a stronger attraction for lithium ions compared to the others.
Like a chemical handshake.
Exactly. Certain molecules, often organic ones like phosphate esters or crown ethers, are designed to bind more strongly to TexFlave, plus due to its high charge density. It's chemistry, not just geometry.
So when we're looking at these membranes, we're judging them on basically how well we pick out lithium that's selectivity.
Right, measured by the separation coefficient,
Hmm.
Celsius, how much better it grabs lithium compared to, say, magnesium or sodium.
And how fast the lithium goes through the lithium flux. And there's always that tension, that trade-off between being really picky and being really fast.
It's a classic selectivity permeability trade-off, yes. And for sources like seawater, the selectivity demand is, well, it's extreme.
How
Okay, get this. In seawater, the starting ratio of sodium to lithium is roughly 6,000 to 1.
6,000 sodium ions for every one lithium ion. Wow.
Right. Now, to make extracting lithium from that viable, to keep the energy cost below about 10,000 kilowatt hours per ton of lithium, which you need for it to make economic sense, the minimum selectivity needs to be over 1,100.
1,100.
Yes. And that's potentially even using a two-stage process. That's the kind of precision we're talking about, just to make seawater a realistic source.
A selectivity over 1,100 sounds almost theoretical. What kind of materials can actually deliver that? And what does that imply about the cost and complexity?
Well, achieving that kind of selectivity really points towards materials with very defined, rigid pathways. And that brings us squarely back to those inorganic solid-state electrolytes, the ICs.
The crystal structures.
Exactly. They're the champions when it comes to selectivity because their crystal lattices have these built-in, stable, perfectly sized channels or bottlenecks for ions to move through.
So the lithium has to kind of hop through this atomic level obstacle course.
That's a good way to put it. We generally group them into three main types: Lisicon type, perovskite type, and garnet type.
Yeah.
In all of them, the idea is that Texli plus dollar can hop between specific sites through these rigid channels, while larger or differently charged ions just can't fit or move easily.
Can you give an example, say, from the Lisicon family?
Sure. Lisicon-type materials like LATP or LAGP, that's lialuminum titanium phosphate or lialuminum germanium phosphate, show amazing performance. The bottleneck size is key.
How amazing.
Well, one study using LAGP reported a separation coefficient, Boy, of $17,900 for lithium over sodium.
17,000.
Yes, and for lithium over magnesium, Textline 2 plus, it was even more staggering, 1,476,000.
Over 1,000,000 to 1 selectivity against magnesium. That's practically perfect identification. How about the perovskites?
Perovskite types like LLTO, lithium lanthanum titanate, are particularly interesting for seawater mining. Their structure involves these interconnected cages. For lithium to move through, it has to pass through a sort of square window between cages, which is at 1.07 angstroms wide. The bare Texli plus ionolators is just small enough, around 1.18 award diameter, to kind of squeeze through.
While bigger ions like magnesium get stuck.
Exactly. And using LLTO, researchers achieved a limb separation coefficient from seawater of 408,943. Again, incredibly high selectivity.
And this isn't just lab stuff, right? I read these are actually being tested in real systems.
Yes, absolutely. There's work being done using LAGP membranes, for instance, for direct metallic lithium extraction from seawater powered by solar panels.
Wow.
And they've achieved lithium purity up to 99.9 weight% using an LLTO membrane in other tests. So the performance potential is definitely there.
Okay, so the ISCs are incredibly precise. They hit those mind-blowing selectivity numbers. What's the downside? There has to be a catch.
There is. The main drawbacks are really about practicality in manufacturing. Making these perfect crystalline structures is complex. It's often labor-intensive, requires specialized, high-temperature equipment.
Meaning expensive and hard to scale up.
Precisely. And maybe the biggest issue. These materials are inherently brittle. They're ceramics, essentially. To get good flux, you want the membrane to be thin.
But thin ceramics break easily.
Exactly. So you have this tension between wanting high flux, thin membrane, and needing mechanical strength and durability. Thicker, more robust structure. Brittleness is a major hurdle.
Okay, so if the inorganic options are super selective but brittle and hard to make, the logical next step is to look for something more flexible, easier to produce in large sheets, perhaps. That must be where the organic membranes come in.
That's right. Organic membranes offer that flexibility, easier processing, potentially lower cost, all attractive for scaling up, but they generally trade away that extreme selectivity.
How do they work then, if not by size sieving those bare ions?
They rely almost entirely on the other mechanism we discussed, binding affinity difference. They use specific organic molecules embedded within the membrane that chemically prefer to bind with lithium.
That chemical handshake again, what kind of molecules are we talking about?
Well, one common class is phosphate esters. For example, tributyl phosphate, TBP, often used with something like iron chloride, textaphyl 3D3, as a co-extractant.
And that combination likes lithium.
It shows a strong binding preference. Hydrogen ions bind strongest than lithium, then far behind are magnesium and sodium. So it can select lithium reasonably well.
But I imagine organic liquids in water might leak.
That's the big stability problem, yes. The liquid organic extractant can gradually leach out into the brine solution over time, reducing performance and potentially causing contamination.
How do you stop your selective chemical from just washing away?
Engineers have developed ways to mitigate this. One approach is the sandwiched liquid selective membrane, where the organic liquid phase is held between two solid ion exchange membranes, physically trapping it.
Containing it.
Yes. Another popular method is using polymer inclusion membranes, or PIMs. Here, the extractant molecule is physically entangled or sometimes chemically anchored within a solid polymer matrix. That improves stability quite a bit.
Okay, so PIMs offer better stability. What about other chemical attractors? Crown ethers always fascinated me in chemistry class, those ring-like molecules that perfectly fit specific ions.
They are a classic example of host-guest chemistry, perfect for demonstrating affinity. A molecule like 12 crown 4, for instance, has a cavity size that's a really good fit for the bare lithium ion, so it binds TexLi++ quite strongly.
Sounds ideal.
But here's a really interesting twist, kind of an aha moment for membrane transport specifically. Unlike just pulling lithium out in liquid extraction, in a membrane, if the binding is too strong, it can actually slow things down.
How so?
If the crown ether, or whatever binder you use, holds onto the lithium too tightly, it hinders the next step, which is releasing the lithium on the other side of the membrane. The ion gets stuck.
Ah, right. It needs to grab the lithium selectively, shuttle it across, and then let go quickly so the next ion can come through. Too strong a grip jams up the process.
Exactly. It's like a revolving door. It needs to catch you, turn, and release you smoothly. If it holds on too long, the throughput drops. You need that Goldilocks affinity strong enough to be selective, but not so strong it kills the flux.
So which crown ether hits that sweet spot?
Well, one study found that while 12 crown 4 binds TexLi++ strongly, something like dibenzo 18 crown 6, DB18C6, actually provided a better balance for transport during electrodialysis. It achieved a Li plus Mg2 plus selectivity of around 24.35.
Okay, 24, much lower than the hundreds of thousands we saw with HESUS.
Orders of magnitude lower, yes.
So the bottom line on organic membranes seems to be much more flexible, easier to process and scale, but that selectivity, especially against ions like sodium, which are chemically similar to lithium, is often nowhere near the inorganic ones.
That's a fair summary. And that long-term stability, the leakage issue, while improved with things like PIMs, it remains a significant concern for real-world, long-duration operation.
Which naturally leads us to think, can we combine them, get the best of both worlds? And that must be the idea behind composite membranes.
Precisely. Composite membranes are exactly that attempt, trying to marry the processability and flexibility of a polymer host matrix with the high selectivity of inorganic filler particles embedded within it, a hybrid approach.
So you mix tiny, highly selective inorganic particles into a flexible polymer sheet.
Essentially, yes. The idea is the polymer provides the structure and ease of handling, while the fillers, which could be LISS, ACs, or even MO, metal organic frameworks, do the selective work.
Now, MOFs are interesting too, known for their tunable pores. How do they stack up against ICs when used as fillers in these composites, especially for that tricky lithium-sodium separation?
That's a crucial comparison. And what the research tends to show is that generally composites using IST fillers achieve higher TexLi plus Textan scale plus selectivity than those using MOF fillers.
Why is that? It seems counterintuitive if MOFs are so tunable.
And it comes back to that fundamental difference. Bare ion size versus hydrated ion size. The ISC fillers, with their rigid crystal structures, often have very small effective pore sizes or channel bottlenecks, maybe around 1.0 to 1.5 angstroms.
Small enough to distinguish the bare lithium, around 1.2A, from the bare sodium, around 1.9A.
Exactly. They can leverage that bare size difference directly through size sieving. Now, MOFs, while tunable, often have larger pores in practice, maybe 3.0 to 9.0 angstroms or more.
Much bigger.
Right. Which means they're primarily interacting with the hydrated ions. And as we established, hydrated lithium and hydrated sodium are very close in size.
Making it much harder for MOFs to tell them apart efficiently based on size alone.
Correct. They might rely more on differences in hydration energy or weaker affinity interactions, which just isn't as effective for line of separation as the direct size exclusion possible in the smaller ONS channels. If you really want efficient line of separation with a filler, you likely need that sub 1.9 angstrom bottleneck.
So ISE fillers seem scientifically superior for the task, but putting brittle ceramic particles into a flexible polymer, doesn't that just create new problems? You still have the overall selectivity flux trade-off, and now you have issues at the interface between the filler and the polymer.
Absolutely. That interface is critical. If the polymer doesn't bond well with the inorganic filler particles, you can get gaps, poor mechanical strength, and the membrane can degrade quickly. Durability is a major challenge for composites, and just mixing the filler in randomly often creates very tortuous interrupted paths for the lithium, leading to low flux.
So it's a tough engineering puzzle. Where do the source materials suggest we go from here? What are the promising pathways to make these composites truly viable?
The research points towards two main strategies. First, tackling that low flux issue caused by random filler dispersion. The key is regulating filler orientation.
Making the filler particles line up.
Exactly. Using techniques like, say, electrospinning to create polymer fibers containing aligned filler particles, or applying external electric or magnetic fields during membrane fabrication to orient the fillers. The goal is to create continuous, direct channels for lithium transport right through the membrane, turning isolated selective pockets into an efficient highway.
Okay, that addresses the speed, the flux. What about the weakness, the durability problem at the interface?
That's the second major pathway. Enhancing compatibility between the filler and the polymer matrix. This often involves chemistry.
Like a glue.
Sort of. Using things called coupling agents, like silane coupling agents, they can chemically bond to both the inorganic surface of the filler particle and the organic polymer chain, creating strong chemical links across that interface.
So better bonding equals better mechanical strength and longer life for the membrane.
That's the idea. Improved interfacial compatibility should lead to much more robust and durable composite membranes.
All right, we've covered a lot of ground in this deep dive. We started with lithium, the white oil, saw its price skyrocket due to demand, forcing us to look beyond traditional sources.
To things like low-grade brines and even seawater, with their unique challenges of low concentration and high competing ions.
Which led us to lithium selective membranes. We explored the two main mechanisms: size sieving, exploiting the tiny bare Texlide plus $, using rigid inorganic structures like ice,
Which offer incredible selectivity but are brittle and hard to make.
and binding affinity, using chemical attraction with organic molecules like TBP or crown ethers in more flexible polymer membranes.
Which are easier to process, but generally have lower selectivity and potential stability issues.
And finally, the composite approach, trying to blend the best of both, but facing its own engineering hurdles in terms of flux and durability.
It really highlights how we're pushing material science right to the atomic level to solve this energy challenge. And remember that benchmark we talked about earlier? That required selectivity. Those put over 1100 just to make seawater extraction potentially viable from an energy standpoint. We're aiming for incredibly high performance.
When you look at all these different membrane types, the ultra-selective but slow ISSs, the faster but less selective organics, the hybrid composites, what do you think ultimately decides which technology wins out?
You know, it's fascinating because the best membrane isn't just about hitting the highest selectivity number in the lab. It boils down to economics, specifically tailored to the source. Meaning, the optimal choice, high selectivity low flux versus lower selectivity high flux, depends entirely on what you're starting with. Treating a relatively clean brine from a salt flat might favor a high flux membrane, even if it's less selective, because the purification burden is lower.
But for something like seawater with that massive sodium background,
For seawater, you absolutely need that extremely high selectivity, maybe even sacrificing some flux, just to avoid being overwhelmed by extracting unwanted salts. The cost calculation shifts depending on the impurity level of your feed stream.
so the choice is deeply application specific.
Exactly. Now, here's a final thought for you to consider. We mentioned seawater holds 230 billion tons of lithium. If, and it's still a big if, these membrane technologies mature, if they become efficient and durable enough to make tapping into even a fraction of that vast oceanic reserve economically feasible, what happens then?
The whole market dynamics could change overnight.
Could completely reshape the global lithium supply chain, potentially stabilizing or even crashing prices, and maybe accelerating the transition to battery-powered everything even faster. That's the potential revolution these tiny membranes hold.